All right, sorry. Thank you again for coming out to my dissertation defense, and which concerns the study of electric field gradients in relation to nuclear magnetic resonance. This is the basic outline of my talk, which I'm going to be talking about initially, just the basic theory of nuclear magnetic resonance and some new results that we have in relation to NMR. Next, I'll be talking about electric field gradients and how we can use first principles calculations in order to predict electric field gradients for experimental purposes. And then after that, I'll talk about a collaboration we did with the Jarvis database at NIST in order to produce the world's first and currently only DFT-based electric field gradient database. And then finally, I'll talk about how we can use these electric field gradient calculations to better understand exotic materials such as iron-based superconductors. Sorry, I have a little bit dry mouth this morning. And so first, just a little bit of basic background on nuclear magnetic resonance, usually the most common type of nuclear magnetic resonance. The effect in NMR is based off of the Zeeman Hamiltonian, which is given here. The gamma here is the nuclear gyromagnetic ratio, I is the spin angular momentum operator, and B0 is an externally applied magnetic field. So if you imagine you have a crystal system full of spin one half particles arranged in any random direction that they like, if you apply an external magnetic field, which is this B0 here, you'll induce an energy level splitting. And the reason for that is because the magnetic moment induced by these spin one half particles will want to align with the externally applied magnetic field. Typically, what's done in NMR is that you apply an excitation pulse with the goal of measuring the transition frequency between these two energy levels. This is the most common type of NMR called spin one half NMR or high field NMR because of the fact that there's an external magnetic field being applied. Now I want to move to another type of spectroscopic technique related, which is a subset of nuclear magnetic resonance called nuclear quadrupole resonance, but based off of an electric effect. This is the Hamiltonian which dictates this effect, called the quadrupolar Hamiltonian, and I'm going to talk about each component here separately. The first component here is the Q, which is the quadrupolar moment of the nucleus. This is an electric quadrupolar moment, not a magnetic moment of the nucleus. This Q, when it's equal to 0, it dictates this quadrupole moment. It dictates the spherical, the spatial distribution of the charge on the nucleus. So this Q equals 0 refers to a spherically symmetric charge distribution, and the spin of that is 1/2, which is what I talked about in the previous slide. Now, what happens when this charge distribution is not spherically symmetric, oblong in this sort of way? Well, the spin will be equal to something greater than 1/2, and the Q will be non-zero. So you can only have this effect when you have a quadrupolar nucleus, greater than spin 1/2. So in the previous case, I talked about how you apply an external magnetic field in order to get preferred alignment of this nucleus. How do you do that in this case for an electrically quadrupolar nucleus? Well, the answer is you apply an electric field gradient. You don't apply it, it's actually induced inside the material. It comes about by the local electronic structure in the crystal. The electric field gradient is defined as the second derivative of the electric potential with respect to position, evaluated at the position of the nucleus. This electric field gradient is being shown here in this cartoon by these pluses and minuses, and you can see here that there is a preferred alignment, this lower energy and higher energy configuration. The important thing to remember about this electric field gradient is that this effect in general is that it is completely intrinsic to the crystal, meaning that you don't have to do anything to the crystal as an experimentalist besides excite it. This electric field gradient is a 3×3 tensor and has therefore 9 components to it. There are a couple other parameters that I want to talk about, which will be important for the remainder of this talk. The first one, the asymmetry parameter, which measures the anisotropy in the system, defined as the XX minus the YY component all over the ZZ component. And then finally, because you have a 3×3 tensor, you can of course diagonalize it. and you can get a set of three principal axes, which are orthogonal to each other. And so I'll talk about this principal axis frame, which is when the system is diagonalized. So the first question you might ask is, I've talked about high field NMR, and I talked about this zero field nuclear quadrupole resonance type of technique. Why would you want to do NQR to begin with? Well, the first answer, and the most obvious answer, is that you don't need to have this high external magnetic field applied. Experimentalists have to apply these massive magnetic fields on the orders of tens of Tesla, and you have to go sometimes to a specialized laboratory just to get these massive magnetic fields. And so without the need of that, it becomes a superior technique in some cases. Another reason is that there's very high specificity in the signals. What I mean by that is that the signals are the fingerprints of the material. If you look at this simulation down here, I have same exact materials using NMR, and then on the right side using NQR, using a powder sample. So they apply an external magnetic field here, and you can see immediately how broad these signals are. Whereas on the right side, where they didn't apply a magnetic field, sorry, this is a simulation where you simulate a magnetic field, you see that the signals are very sharp, no broadening whatsoever. And so immediately you can see that these signals are highly specific to the material, and that's why some people, quote unquote, call NQR frequencies the fingerprints of the material. And another reason why you may want to do NQR is that there's a lot of materials which are NQR active, meaning that there are many nuclei with isotopes which are quadrupolar in nature. So now I pose another question. What if we have both cases? What if you have a quadrupolar nucleus in the presence of a magnetic field? In this case, you have, well, there's no name for it, it's quadrupoles in a magnetic field. And this is some recent work that we did that we submitted to Physical Review B, and we received really good positive reviews, which I'll recommend publication. And I resubmitted it last week, so we're very confident that it'll be published very soon. And so, as promised, if you have quadrupoles in a magnetic field, you have both effects. Here you have the Zeeman Hamiltonian, and you have the quadrupolar Hamiltonian. So let's just focus on the Zeeman Hamiltonian first. If you try to diagonalize this for a spin 3-half particle, you try to diagonalize it, you have 4 energy levels. When you get the energy levels, you get 4 equally spaced energy levels. On the other hand, if you just focus on the quadrupolar Hamiltonian, you also get 4 energy levels, but they are doubly degenerate, meaning there's 2 energy levels here and 2 energy levels here. And so one of the ways you can lift that degeneracy is by introducing a magnetic field. And that's what happens here. These 2 levels split into these 2, and these 2 levels split into these 2, lifting that degeneracy. Thinking about it the other way, if you have the quadrupolar Hamiltonian, then you introduce, if you have a quadrupolar particle in a magnetic field and you introduce an electric field gradient, you can say that you can shift the energy levels, meaning that you have 4 energy levels which are now not equally spaced. And the benefit of that now is that you have 6 unique transition frequencies as a result of that. And so how do you perform an NMR measurement in this case? This is the dominant Hamiltonian, which is the combination of the Zeeman Hamiltonian and the quadrupolar Hamiltonian, and you have these 6 unique transition frequencies. How do you measure them? Well, what you do is you apply a perturbation. And the perturbation in this case is the excitate, is a linearly polarized radio frequency pulse given by this Hamiltonian here. The key thing to remember here is that actually these 6 transition frequencies are not created equal. When you send in this linearly polarized radio frequency pulse perpendicular to this magnetic field V0, you will only be able to measure 4 of these 6 transition frequencies. Whereas if you apply this excitation pulse parallel to the magnetic field, you're only able to observe 2 of those 6 transition frequencies. For that reason, we call these the parallel transitions, and we call these the orthogonal transitions. Now, there's a bunch of different features that we can talk about that we found in our research regarding this system. First, we need to define this dotted line here, which refers to the Zeeman frequency. The Zeeman frequency is proportional to the Zeeman Hamiltonian equal to negative gamma V0. The first feature we can look at is that the lower transition frequency, the lower frequency and the upper satellite frequency, the lower satellite frequency and the upper satellite frequency, their average is exactly that of the Zeeman frequency. We can look at the average of the lower satellite and the central transition frequency. Its average is half of the first parallel transition. And then similarly above here, we have that the average of the central transition frequency and the upper transition frequency is half of the second parallel transition. Why am I talking about all of this? The key thing is the useful of this for an experimentalist especially is that if you're able to measure 3 of these transitions, any 3 of them, using these relationships, you're immediately able to determine the other 3 using those relationships. There's a lot of other work that we did in this part of the research, and the key hallmark of this research was that we were able to determine the exact analytical expressions for the transition frequencies and for the spin angular momentum matrix operators given here. These are important because we also derived a formula for the observed signal, which makes use of these operators here, these matrix elements here. Another aspect of this project is that we were able to use it to study materials such as iron-based superconductors. I have a lot to say about iron-based superconductors later in the talk. I'll just briefly go over the basic unit cell of iron-based superconductor, which is comprised of these 4 iron atoms in this square lattice. Each of these iron atoms has its own magnetic moment, and they're oriented in this stripe-like antiferromagnetic configuration. This stripe-like antiferromagnetic configuration results in an extremely large magnetic field on this arsenic atom, which is placed a central distance above the iron plane. There's 2 things going on here. This arsenic atom has a quadrupolar nucleus, and this large internally produced magnetic field is absolutely massive. It's on the order of a Tesla. And so it is perfectly suited to be studied by this research that we did of quadrupoles in a magnetic field. And so going back down here, I have this simulated spectrum that I calculated for a very specific value of for asymmetry, quadrupole coupling, constant internal magnetic field. We can now see the analysis. We can see how this is mapped onto a real experimental spectrum. And so on the right side here, I have powder sample data of 0 field NMR done for barium iron to arsenic 2 and calcium iron to arsenic 2. And you can immediately see that these 3 peaks here correspond to these 3, the central and the lower and upper satellite transition frequencies. This is data that I got from literature, and I fitted them myself. The key thing that we did here was that we were able to extract 3 of the important parameters from the system. The 3 parameters being the quadrupole coupling constant, which is proportional to the VZZ component of the electric field gradient. Also the internal magnetic field, one that's produced over here, and also eta, which is the EFG asymmetry parameter. We were able to fit these. We were able to fit the data, extract the transition frequencies, and solve using our equations. We were able to easily solve for these components here. The key thing to remember here is that this was done at 0 field, no external magnetic field. It was only internally produced, and this was done for a powder sample. You don't need a single crystal to do this type of spectroscopy. However, people still do that. And so these other data points here represent data from literature where they used a single crystal and they also used an external magnetic field. And so what you have to do in this case in order to extract these 3 parameters, take your single crystal, have your external magnetic field, you rotate it, make a measurement, rotate it, make a measurement. You have to get it to function as a function of the rotation angle in order to be able to extract all 3 parameters. But as you can see, sometimes it's not even reliable. You can't even get all 3 parameters using that technique. And so in some cases, you may argue that 0 field NMR is the superior technique for studying these materials. And so now we arrive at the problem. In the previous slide, I talked about how I took an experimental spectra and I was able to extract the EFG and the magnetic moment from the system. But what if I presented you with an unknown material? How do you know where those frequencies are? You need to know the electric field gradients. And because NQR is so specific, it has such high specificity, such sharp signals, it's really hard to find them. And so this is the main problem. Here, this quadrupolar moment is known. It's been measured to very high precision for almost all isotopes, so it's not really a problem in that regard. The problem is the electric field gradient. It's VXX, VYY, and VZZ, the principal components of the electric field gradient tensor. How can we calculate these? And so that brings me to my next topic, where I try to use density functional theory in order to calculate these electric field gradients. We wanted to see in particular, how well does DFT perform in being able to calculate electric field gradients and how close can they get to experimental value. So for this project, I performed calculations using the PAW methodology and the LAPW methodology. I unfortunately don't have too much time to get into the meaning behind these 2 methodologies, but keep in mind that LAPW is an all-electron methodology. PAW is a methodology which uses a pseudo-potential, which is able to transform into a full potential. So I wanted to study in particular how the PAW pseudo-potentials performed in being able to predict these electric field gradients. This resulted in a publication what feels like decades ago. It was just 2019. And I encourage you to go take a look at this paper and see what we did, but I'll talk about it now as well. So like I said, using the PAW methodology, we use FAST, which is the most popular software to use for using this methodology. You're given a bunch of different pseudopotentials. Each of these pseudopotentials have their own advantages and disadvantages. For example, the hard pseudopotentials have a small radial cutoff of the potential. They're more accurate, but they take much longer to compute. Whereas the soft pseudopotentials have much larger radius cutoff. They're less accurate, but they're much faster to perform as well. There are also the PV and the SV pseudopotentials, and these treat valence electrons differently. For example, the PV treats the P electrons as valence electrons. There's also the AE pseudopotentials, which treats all electrons, but they only do that for the first three elements on the periodic table. So hydrogen, lithium, and whatever the third one was. Yeah, so in this case, I want to talk about how we did calculations for the sodium nitrite one, for sodium nitrite. And in sodium nitrite, we have the quadrupolar nucleus, which is 14 nitrogen. And so what I did was I did calculations for this material by holding the nitrogen, by varying the pseudopotential for nitrogen for all these different pseudopotentials, but holding the sodium and the oxygen constant. And these are the results. On the y-axis, we have the VXX and the VYY components. And on the x-axis, I have the VZZ component. And what you immediately see is that there's two clusters. The reason for that is because I'm plotting the VXX and the VYY together on the y-axis. And you can see that these different colors correspond to the different pseudopotentials that we vary for the nitrogen site. And so what can we say about this? We have the experimental value, which is going over here for the VXX and the VYY components. And we can say that these calculations were precise, but not necessarily accurate because of the fact that they clustered with each other, but they weren't quite near the experimental value with regards to the error bar. There were also previously done LAPW calculations and they were consistent with my PAW calculations. Moving on to another site of the same material, sodium nitrite. This one, we varied the sodium 23 site using the different pseudopotentials. And you can see a very different scenario here. These calculations were not necessarily accurate, and you can see that they flanked both sides of the experimental value. And so these calculations, you can say, were not necessarily as accurate, but you were able to create a window of accuracy, essentially. I did my own LAPW calculations using Beam 2K, and you can see that they clustered somewhat near the PV and the SV pseudopotentials. Moving on to the other material, which is titanium oxide, we looked at the 47 titanium site, and this one was an interesting calculation because, as you can see, I was able to predict the experimental value almost pretty much exactly within the error bars. You can see that the PV and the SV pseudopotentials are right on top of that, which is great. And I even did my own LAPW calculations. You can see here, we're also smack dab right on top of my PAW calculation. So they were consistent and they were able to predict the experimental value. The problem is that the PV and the SV pseudopotentials were accurate, but the standard pseudopotentials, the ones that don't do anything special, were not able to predict. Thanks for joining us. So yeah, the problem here is that if you have an unknown material and you're able to perform these calculations, how do you know where your experimental value is? Is it clustered with the PV and the SV, or is it clustered with the standard pseudopotential? So that's also a problem that arises from that. And lastly, I want to move on to this copper oxide, which is a very difficult material to converge. And you can see here by the result that it's also a very difficult material, and it's been used for the better part of the past 30 years as a litmus test to better understand, to test new features in density functional theory. Immediately, you can see that there's no interesting clustering going on. They're clustering with themselves in their same pseudopotentials. And you can see there's different calculations using the LDA XC functional approximation and the GGA XC functional approximation, and they're also scattered about. And I even did my own LAPW calculations, which also was clustering with those PV and with the PAW pseudopotentials. The most successful one was this PVE0, which is a hybrid functional using GGA and LDA approximations in conjunction. That was the most successful one, but even then, they were not able to predict experimental value within the error bars. And so what can we say about these calculations? Can density functional theory predict electric field gradient calculations? The answer is not consistently, but they are able to give you a window of accuracy, meaning if you are an experiment, if you put yourself in the shoes of an NQR spectroscopist and you have an unknown material, you have this massive frequency search space you have to use in order to determine these frequencies. You have to go through the whole search space in order to determine the frequency. But if I can give you, let's say, worst case scenario, 50% off of that whole search space, I've already saved you a bunch of time trying to find those frequencies. So from that perspective, you can say that they're useful. So now I want to move on to the next topic, which was developing the world's first and largest electric field gradient database. The reason we wanted to do this is because performing these calculations are very lengthy, and we wanted to see how can we automate them and give them to the general public, particularly focused to the scientists who are trying to find these frequencies. How can we give them access to high quality density functional theory calculations? And so that comes in the joint automated repository for various integrated simulations, which is the Jarvis database hosted at NIST and founded by Dr. Kamal Chaudhry, who is here with us today. And so we collaborated with Dr. Chaudhry in order to develop this database. It is a great database. It doesn't just do DFT, it has a whole bunch of different components to it as well, running automated fast calculations. This collaboration resulted in a publication a couple years ago, and I encourage you to go take a look at it. I also encourage you to go to Jarvis and take a look at the values that you can look at the data that's available there for free to the public. So I just want to briefly go over what kind of stuff that you can, when you go onto Jarvis, say you search for a material, this is the landing page that you find. I chose here barium iron to arsenic 2 on purpose as to allude to the next topic. If the EFG has been calculated, we weren't able to calculate the EFG for every single material. Well, it wasn't necessary because for some crystals, there's cubic symmetry, in which case we have a 0 EFG. But if an EFG was calculated for this material, you'll see this tab here, EFG, and when you click on it, you're presented with the full EFG tensor, the full 3x3 tensor, giving you all values that you need. And this is the first time it's been produced. The simplicity of it, just clicking the button, there you have your EFG tensor for any material. It's very powerful. And so when we performed the calculation, we had about 10,000 or so materials that we did calculations for, and we wanted to validate how good are we consistent with previous DFT calculations. And so that's what we did in this plot here. We scoured the literature for every possible DFT calculation that we could find. And what we have here on the y-axis is the current work, our calculations. And what we have here on the x-axis, we have previously calculated DFT values. And you can see here with this line fit, it's actually a very good fit. And they're fairly consistent with previous calculations. On the other hand, we also want to ask, are these any useful? Are these calculations useful at all? Are they able to come in within a good reasonable range of the experimental values? That's what we're showing here on this plot. This is our calculations. And on the x-axis, we have the experimental VZZ values. And you can see here, they're also a good fit. And so the database is viable, we believe. There's a lot of other interesting statistics that we did for this paper, and I encourage you to go take a look at our paper. It's a fantastic paper, and I don't have too much time to talk about it, unfortunately, but yeah, I encourage you also to visit Jarvis and see what you can do on there. There's a whole bunch of stuff on there. It's constantly being updated. So yeah, it's a fantastic database. So now I want to go to the last topic, which is how we use these electric field gradient calculations to better understand iron-based superconductors, which I briefly touched on earlier. Iron-based superconductors are a newly discovered class of superconductors. They were discovered about 15, 20 years ago. And the interesting thing about them is that their superconducting mechanism is not known. They exhibit unconventional superconductivity. They don't follow the current BCS theory of superconductivity. Now, the way that the crystal structure is set up, which I talked a little bit about earlier, it is perfectly suited to be studied by nuclear magnetic resonance. And so here are the different families of iron-based superconductors. Here they have the 111 and the 122s. These are named after their stoichiometry. So it's sort of a colloquial way to refer to them. Each of them, there's a bunch of different families of iron-based superconductors, but the key thing is that there's a common motif that you can see throughout all of them, and that is this iron plane and this atom above the iron plane. This atom above the iron plane could be a chalcogen or a pnictogen, but I'm going to refer to it as just arsenic in this case for simplicity. And what you can see here is that These four iron atoms, as I talked about earlier, each of them has their own each of them has its own magnetic moment, and they're oriented in this very specific stripe-like antiferromagnetic configuration, which results in this massive magnetic field at the arsenic site. Again, arsenic has a quadrupolar nucleus with high relative abundance, and this magnetic field, which is being internally produced, makes it perfectly studied by NMR of zero field NMR using the research that we developed earlier in this talk. I'm going to be focusing specifically on this 122 family, but our results can be applicable to any of these families. And so this is the phase diagram for an iron-based superconductor. On the y-axis, we have the temperature, and on the x-axis, we have the doping with cobalt. This material is barium-122 cobalt doped. The reason that I'm going to be referring to this material for the remainder of this talk. The reason that you would want to dope these materials is clear from this phase diagram. The more you dope it, that's where the superconducting dome appears, and so that's why this is done this way. There are three phases that I'd like to talk about, though, which are general to these materials. The first one is being covered by the green. It says paramagnetic up there. The first phase, which is the high temperature phase, is the paramagnetic phase. It is this phase which is tetragonal, meaning that the sides of the lattice are equal to each other. In this phase, there's no magnetic ordering. The next phase, which is the low temperature phase, is the antiferromagnetic phase. In the antiferromagnetic phase, there's two critical transitions that occur. The first transition is the orthorhombic transition. You can see here, if we're just looking at the x equals 0 bit, you can see here, there's a small bit where it's tetragonal, and then that transition into orthorhombic occurs at that temperature. The key thing to remember in the antiferromagnetic phase is that this is where we exhibit the stripe-like antiferromagnetic configuration. Finally, there's an intermediate phase called the nematic phase, which was completely unexpected when it was discovered. And you can see here that you can only get this phase by doping the material, and it comes up in this small little sliver here. As opposed to the paramagnetic to antiferromagnetic transition, there's only one transition that occurs here, and that is just a structural transition from tetragonal to orthorhombic. The result of this is that the crystal symmetry changes, but also there's no magnetic transition. That's also a key thing to remember. And so that the relationship of this phase and how it relates to superconductivity is a major question in these materials. Finally, a really critical point is that there are fluctuations in these materials in all of the different phases, meaning that there's movement in these iron magnetic moments, they're not static. It has been conjectured that these fluctuations have been tied to are considered to be the pairing loop in superconductivity. And so there's a lot of research going on to better understand these fluctuations and how exactly they contribute to the superconductivity in these materials. And so I want to now talk a lot more about these spin fluctuations, because they're very important in understanding these materials. And there's two types of spin fluctuations. The first one are the spin space fluctuations. The spin space fluctuations, well, here is the original static case that I have here, but the spin space fluctuations occur in the following way. You can see here that they can move in the iron moments, the magnetic moments can orient themselves in any which direction that they like, such that they remain collinear with their neighbor. That is, they remain parallel or anti-parallel with their neighbors. The thing about these fluctuations is that these are long-range order fluctuations. There's a low energy cost. It doesn't take much to get them moving in this particular way. But the key thing to remember is that the magnetic order is not changing. What I mean by that is, you can see that the system is ferromagnetic along this axis, but it remains anti-ferromagnetic along this axis. Now, because the magnetic order itself is not changing, the orbital order is not changing because they're tied to each other. And when that orbital order does not change, the electric field in the system is not changing, and therefore the EFG is unaffected. This is a very critical result of this that we should keep in mind later from the talk. And you can also see that the internal field varies between positive and negative. It can point in any random direction. And so if you have sufficiently fast fluctuations, and these fluctuations are in fact fast, they average out very, very easily. The second type of fluctuation are the real space fluctuations. And these are fluctuations of the magnetic order. Specifically, what I mean is that you can see here initially, at the start of the animation, that there's antiferromagnetic along this axis. But at the end of the animation, you can see that it's ferromagnetic along that axis. And so the ferromagnetic direction and the antiferromagnetic are actually changing with this type of fluctuation. The key thing to remember here is that because the magnetic order is changing, again, because the orbital order is tied to the magnetic order, the electric field gradient is affected in this case. So this is very critical. In the spin space fluctuations, the EFG is not affected, but in real space fluctuations, the EFG is affected. And so the goal of this project was to develop a quantitative model of spin fluctuations using previously performed NMR experiments and also my own density functional theory calculations. This resulted in a publication last year in Physical Review B, so I encourage you also to take a look at that paper as well. And so here's the problem that we have at hand. Just in general, talking about the paramagnetic phase, I said before, it's tetragonal, it has tetragonal symmetry in that phase. And because of that tetragonal symmetry, we expect the EFG asymmetry parameter, defined as this, AA, BB, and CC referring to the crystallographic axes. Because there's tetragonal symmetry, we expect this eta to be equal to 0. However, a recently performed experiment around in 2018 showed a very interesting result. They found that eta was not 0 in the tetragonal phase. So this is their data here, and you can for this cobalt dope barium 122, you can see on the y-axis eta here, and on the x-axis we have temperature. And these little arrows here refer to the structural transition between orthorhombic to from tetragonal to orthorhombic transition. And these different colors refer to different cobalt dopings. The key thing to remember here is that none of these values are 0 within the error bars. In fact, they're all small but non-zero above 0. That is the critical thing because they should be 0 by symmetry. The thing that you might, the low-hanging fruit that you might say, the reason that why there is anisotropy in the system, you can say is because maybe there's some external strain in the system. The paper was very clear to account for that. They said that they didn't put any glue on the crystal or hold it in any funny way that would induce a certain strain in the system. And so we come in here and we have a different interpretation. We believe that the source of this asymmetry is due to spin fluctuations. And so now I'm going to take a deep dive into what exactly I mean by that. Remember that I said that spin space fluctuations, these long range fluctuations, are very fast. In fact, they've been measured to be very fast, and they're much faster than the NMR time scale. But also, remember I said that the magnetic order doesn't change in the system, and therefore the EFG is not affected. So you can immediately rule out these types of fluctuations as being the possible culprit of this EFG anisotropy that was measured. But the fact that they measured a non-zero eta in the paramagnetic phase, it directly implies that there is a broken tetragonal symmetry. And what could be breaking that tetragonal symmetry? Our answer is that these real space fluctuations are breaking the tetragonal symmetry. As I said, because the magnetic order is changing in the system, that is directly affecting the EFG. And so the implication of that is because they measured using nuclear magnetic resonance, it must mean that there is a slow tail, meaning that these frequencies, these rotations, the frequency of them are measured slow enough to be captured by an NMR probe. And these are the fluctuations that are breaking the tetragonal symmetry. And because of this, NMR is also the ideal tool to probe these fluctuations. As I said earlier, these fluctuations are important for better understanding superconductivity in these materials. And so here's the approach that we took. We wanted to use density functional theory in order to determine an effective magnetic moment. That is what the magnetic moment would be on the time scale of an NMR measurement. And so what we did was we calculated the electric field gradient as a function of the iron magnetic moment for different cobalt dopings. We did calculations in both the tetragonal and the orthorhombic phases, but with antiferromagnetism turned on, critically because we wanted to see how this magnetic moment changes. And so we calculated these EFG calculations and we tuned down the iron magnetic moment by using Hund's rule couplings. What I mean by that is in practice, we introduced a scalar in front of the spin exchange part of the XC functional. Doing that, it allows you to lower the magnetic moment. This is a way to simulate the spin fluctuations. Basically, what I'm saying is that when you don't lower the magnetic moment, you have 0 fluctuations. When you have a lowered magnetic moment, you have high fluctuations. So it's a simulation of the spin fluctuations without actually performing a dynamic calculation. And so here are the results of that calculation as promised. Here on the y-axis, I have the EFG asymmetry parameter, and on the y-axis, I have the iron magnetic moment. And you can see that it's been scaled down in a way. And we did these calculations again for different cobalt concentrations, and also for the orthorhombic and also the tetragonal phases. And here are the experimental values from that paper that I was showing earlier for these values. This is the full data set. It's not very interesting because it's zoomed out. Also, don't be too alarmed by this continuity here. This is just the case of when VCC is equal to 0. Approaches 0, that is. This is a zoomed in view of that previous plot, and this is where all the interesting stuff is. So what I've plotted here is the experimental eta values that were measured from that paper that I showed earlier. You can see again, they're supposed to be 0, but they're not 0 because that's what they measured. But I've also plotted them at the magnetic moment equal to 0. I did that because that's the magnetic moment that you would get if you try to get a magnetic moment for neutron scattering in the paramagnetic phase, you wouldn't get anything out of it. But I want to know what the magnetic moment is associated with nuclear magnetic resonance. NMR using this technique you can't measure the magnetic moment using this technique. And so what we want to do is I want to take this DFT calculations, the fifth here, and using these EFG calculations, using these EFG experimental measurements, I'm able to extract an effective magnetic moment, which corresponds to these intersection points here. These are the effective magnetic moment that you would observe on the NMR timescale. I did the same exact thing for the orthorhombic phase here. Again, this was plotted originally against the magnetic moment measured by neutron scattering, but I want to know the magnetic moment according to the NMR timescale, which is on that intersection point. Now, I really want to hammer this point home. So what I'm plotting here on this plot are the intersection points of this plot here. So these 3 points here are corresponding to these guys here, which I'm calling here NMR plus DFT because it's a combination of the two. On the this blue line here corresponds to the magnetic moment that you would get from neutron scattering, which would of course be 0 because neutron scattering has a very long time scale, considered infinitely long. The averaging effect is enhanced. Averaging of the spin fluctuations over a long period of time is an effect, so you get on average a 0 magnetic moment. And so the interesting thing that you see here is that these NMR plus DFT values are larger than that. And you expect that to happen because nuclear magnetic resonance has a lower transition, has a faster probe time, faster time scale is what I'm trying to say. And so there's less time for it to be averaged out. So we can even look at the calculation at the measurement from the orthorhombic case here. So this red value here corresponds to this intersection point right there. This blue one corresponds to the magnetic moment measured on the NMR timescale from neutron scattering. And again, you can see that our value is larger than that from neutron scattering. Again, because of the fact that the NMR timescale is slower than that of neutron scattering, so there's less of an averaging effect. And then to really, really hammer the point home, I took a measurement from X-ray emission spectroscopy. X-ray emission spectroscopy is considered an instantaneous time probe. It's much faster than both NMR and neutron scattering. And you can see here that their measurement of the magnetic moment is much higher than any of our measurements here. And we expect that to happen because again, there's a smaller averaging effect, and so you get a much larger magnetic moment out of that. And so what can we take away from these results? Firstly, is that if you're going to compare between different values, the timescale of the probe matters. But also, one of the key things that we found is that there are slow real space fluctuations present in the paramagnetic system. This is a very critical discovery because of the fact that it's in the paramagnetic phase as defined, you don't expect there to be any magnetism, but our claims is that there is some residual antiferromagnetism in the system in the paramagnetic phase, and that has direct implications towards superconductivity. The question between magnetism and superconductivity is something that's it's a big question, and because we found this residual antiferromagnetism in the paramagnetic phase, which is where superconductivity emerges, we believe that there's a lot more that can be said there. Again, we published the paper last year, so I encourage you to go take a look at that. And so just to wrap up this talk, what we have is that in the first part of the talk, I talked about how we can use density functional theory to predict electric field gradients, and you can also calculate into our frequencies, which can help experimentalists. Talked about how we developed the first electric field gradient DFT-based database in collaboration with Jarvis NIST. And then finally, I talked about how we can use electric field gradients in order to study these exotic materials such as iron-based superconductors. And with that, I'd like to thank you for your time. There's a whole list of people I can thank. I don't have time to thank everyone. I, of course, have to thank my funding sources, because without them, they put bread on the table. I'd like to thank my family who came out, they've been supporting me all these years. My mom flew in from Jordan this morning, which is insane to me. She's dealing with the baby niece right now. And yeah, so all my friends in here, thank you for coming out, and everyone on Zoom as well. Thank you so much. And with that, I'll take questions from you.
So again, this is a public defense, so we're gonna let the public go first, and then we'll let the committee go.
Yeah, thank you for your presentation. I guess, what are the next steps of the research, and are there any kind of industry applications that could be derived from this?
That's a great question. So in terms of the EFG calculations, we can talk about how so my EFG calculations were completely static. These situations are not, these crystals are in reality are not static. There's a lot of dynamic things going on in there. In terms of thermal motion, in terms of spin fluctuations like I was talking about. So I believe that the next step to do in these calculations is really to include the dynamic effects of these materials in the calculations to see how the EFG changes. And I believe that can get you closer to measuring, to calculating accurate experimental values. In terms of the database stuff, so one of the things about the database is that because they're standardized calculations, you won't necessarily always get close to the experimental value. And I don't really believe that's the goal of the database. I believe that the goal of the database is to provide for the first time a massive data set. And we live in the world of AI and machine learning now. And with that, you need a massive data set. And I believe that what we provided for the first time is to develop models in order to figure out what sort of trends that we have in these materials. And in that, that can also help expand upon trying to do predictions for materials as well. These iron-based superconductors, I mean, we still don't know the superconducting mechanism. There's a lot of work to be done. Actually, I believe I have a backup slide for that. There's two materials I didn't talk about: sodium iron arsenate and lithium iron arsenate, which also exhibit this EFG anisotropy, this unexpected anisotropy in the paramagnetic phase here. See, both of them have also this beta value, which is small but non-zero. And so we want to study these guys as well to see if our conjecture is true across different materials as well. Lastly, there's also iron-based superconductors, which don't even have a magnetic order, which is known. And you can see here from these nuclear magnetic resonance spectra, there's a big transition frequency. There's a big phase transition right there. No one knows what that phase transition is. There's some sort of unknown C4 symmetry that's being broken there. And there's some unknown transition as well. And so trying to understand those and see how they play into our conjecture as well is also really important. To answer your question about the industry, if someone can find a superconductor, which is room temperature, ambient pressure, you've solved the energy crisis. You've saved the world. So that's really the holy grail of superconductor research. If you can do that, you're a trillionaire.
That's why I asked the question.
Very good question, thank you.
Other questions? Online? Okay, so now it's the committee's turn to ask questions.
Go ahead. So about the using X-ray emission spectrum, why was the need of using that instead of EFG, and how does it complement each other?
The X-ray emission spectroscopy stuff, I mean, that was just a measurement. I just kind of did that as a way to really hammer home the point of like the importance of the time scale of the probe. So like NMR time scale, the neutron scattering is essentially an infinitely long time scale of the probe. NMR is a little bit faster than that, but X-ray emission spectroscopy is instantaneous. And so you can essentially say that you're not capturing the dynamic effects of the system using X-ray emission spectroscopy, which is why you're getting this larger magnetic moment. I didn't use it at all for anything else in my research, but it was just really to hammer home this
That's
point.
why I was like, why X-ray emission suddenly, right? So I was like,
Right, yeah.
intrigued by it.
Yeah, it is interesting, but it really ties together everything, because when you're thinking about timescales and you want to think about probes which have different timescales, this is the fastest one that you can get, and it doesn't capture any of those dynamic effects. It's a snapshot is what it gets. the way I think about it is like, imagine if you were, I mean, you're looking at one of these guys, it's literally capturing just a snapshot of this GIF right there. That's all it's getting, because it's like so instantaneous.
If you go back to the same, oh, go ahead, Hera.
Very nice results. I like it a lot. And let me start by this database. Very impressive. So for some material, you do notice when you compare to other independent calculations or experiments, your results for the gradient, right, is on the like overestimates. Sometimes it's on the lower side. Do you see any systematic, observations say, oh, for these group of materials, we tend to go higher, and for those or it's completely random, no understanding yet?
That's a really good question. In terms of a large scale approach to the trends, in terms of a large scale trends, we didn't see anything. We didn't look for trends across different materials. We did see that although we did find a very important thing, an important thing to remember about these calculations is that they were performed using relaxed structures, and they were automated using the standard pseudopotentials, which are recommended by VAST. But one of the things that we found, for example, here, this is the scandium material. Scandium is an HCP structure. And we see here that using the Jarvis calculated the C over A value and the experimental C over A value, there's a big discrepancy in the EFG that's found there. So while we didn't find large trends across different materials, but we want to keep in mind that the structure is also very important in these systems, especially for systems where the EFG is highly affected by structural changes like that. I don't think I answered your question totally, but I think there's work to be done though. To find trends across different materials, I totally agree that there's actually a lot of work to be done there in that regard.
Igor, do you have questions?
I do. So on that question that Erhai just asked, he asked about trends using Jarvis and using a relaxed structure. So you have two papers on this. One's really going across lots of materials in the relaxed structure. You have another set of data that you took previously done with the different pseudopotentials. So for those that work with the pseudopotentials, one, did you work with a relaxed structure? And two, why did you choose those particular set? I mean, in Jarvis, right, you just took everything you got. You just take everything and let's do all the calculations. The previous work, you didn't, of course you couldn't, but why did you choose the materials that you did in the previous work?
So there's two answers for that. The goal, again, was experimental prediction. And so we chose materials which had previously computed, previously measured electric field gradients from very, very highly reliable experimental predictions. And so we were able to take those NQR frequencies and convert them to EFGs and comfortably compare them. So I wanted to see how well were my calculations doing in comparison to that. And for that reason, we didn't use relaxed structures. We could have used a relaxed structure, but we wanted to see exactly, if we used the exact crystal parameters at that temperature that the NMR experiment was performed, how well would they compare to each other? And so we picked those materials which had reliable crystal structure data and reliable EFG data as well from experiments, so that we can compare them holistically and fairly to each other.
And did the temperatures matter in those experiments that you took? I mean, did you choose? What were the parameters in the materials that you were trying to choose?
It's a good question. That's a funny question actually, because initially on the project I was using crystal structure data from non-equivalent temperatures, and the values were completely off. Once I moved closer to the temperature range, I started seeing better agreements. But for some systems, yeah, it can totally affect, especially if the crystal structure is totally altered by the temperature. If there's a phase transition, for example, if there's magnetism, for example, it can totally affect the difference totally affect the agreement in the system.
So for those previous measurements, sorry, I'm the only one asking questions, but I'll go ahead. So for the previous ones that you did, and you said that you chose ones in which you they were experimental values. But were they all the same kind of material? Was there any
Oh, there was-
range over them? And what was it, again, well, there was some choice, there's still even more experimental values you could have chosen. Why that said?
Well, if I understand your question correctly, like why am I choosing those materials specifically? There were reliable experimental data, but also reliable DFT calculations as well. These materials have been calculated for the better part of 40 years by some of the pioneers of DFT. And so using these calculations, they've done it for different XC functionals, for different pseudo potentials. I wanted to see where my calculations fit in within those ranges as well. They also did calculations using atomic orbitals as a basis set. I didn't even talk about that here because I didn't have time for it. But those materials had an absolutely massive, a relatively large data set available for me to compare to.
Go ahead, Erin.
So I have the first part, the NMR plus NQR,
Mhm.
the nice paper you published in PRB.
Thank you.
I try to imagine, like visualize what is happening. So you made the point that now you have an electric dipole moment for your nucleus, right? There is
Like the quadrupole moment.
yeah, quadrupole moment. Thank you. The charge distribution develops some multiple moments, right?
That's right.
And on the other hand side, we do know that it has a magnetic moment,
Mhm.
right? Now, if I understand correctly, the spin and charge within, or density and the spin within the nucleus, they are coupled somehow. So don't you also expect that you have some higher magnetic moments as well for your nucleus? And if so, presumably the experiments are so precise nowadays. Do you expect something that you can extract from that as well?
That is a great question, and I have wonderful figures talking about that. I didn't put any of them on here.
Okay,
But that is a very good question. In fact, the geometry of when you excite this, you use a radio frequency to excite this nucleus. You have an observed magnetic moment out of it from the nucleus. This observed magnetic moment has very important geometrical consequences. In fact, I kind of touched on it a little bit. Some of those transitions are not observable if you excite parallel to the magnetic field, and sometimes orthogonal to it. But in particular to the observed magnetic moment, not the magnetic field, the observed nuclear magnetic moment, you can look at the Rabi frequencies. You see the geometric distribution of that, and you can tell exactly which signal will be strongest when in which direction in relation to that. So yeah, there is a coupling going on in that scenario, and I wish I put that as a backup slide. But
He's not really asking that, actually. He's asking what is the higher order term, magnetic order, like you do multiple moment expansion, right? So it's a first order
I think it's
dipole, you're
just
talking about.
higher order because magnetic moments are by definition.
Right, you
oh,
would,
sure.
Well,
If you
they're
went for higher spin, that's correct. But we're using spin 3/2, so I think that, if I'm not mistaken, the expansion stops at quadrupole for spin 3/2. If I'm not mistaken on that, I may have to check on that though. But in general, yes, that there would be higher effects there.
One more question, sorry.
no.
So
So we have this room
a
until
lot
12.
of,
so
a few slides mentioned that your calculation can be compared with the experimental value for the, say, VZZ or, I don't remember which, exactly. How, yeah, experiment data. How do people measure the electric field gradients in experiments?
Well,
And
there's,
how accurate are they?
So there's many different ways to, you can use Mossbauer spectroscopy, for example, to measure EFG, but the technique that we're compared to is always NMR in this case. So in NMR, you have the transition frequencies that you extract, that you measure, you get the transition frequencies, and the transition frequencies directly are related to the electric field gradient. And what we did actually in our first project is we had analytical formulas directly to that give the NQR frequencies, the NMR frequencies technically, and you can use those exact formulas to extract the EFG from that. NMR it's a very refined technique, very exact, so you can extract the electric field gradients from really good precision actually.
For example, this could be applied to I would say, iron-based superconductors and really measure the fielding.
Absolutely, yeah.
Okay.
In fact, that was the point I was making in this plot here. This is actual NMR data. This is actual NMR data that I pulled out from experiments. I fitted these data points, but this is what they gave on the literature. These were done at cold temperatures, and they were done using a powder sample. All they did was excite the system. And so using these, we were able to extract not only the EFG easily, we were able to extract this new Q, which is proportional to the BZZ component. We were able to extract this eta, which is the EFG symmetry parameter. And we were also able to extract this internal field easily using the equation that we derived. You can do it with high field NMR with an externally applied magnetic field, but it complicates the matter a little bit. You have to find the transition frequencies as a function of rotation angle of the crystal with respect to that external magnetic. So
But this is armed with knowledge of your work.
these,
Before that, so like, look at, say, like, I'm very naive, I look at these green curves, I have no idea of what the eta is or VQ is. You have to do some modeling, and that modeling require the knowledge of your, say, your PRB work.
that's right, yeah.
Okay,
It requires a little bit of
okay.
advanced knowledge.
That's nice.
But at the end of the day, you can technically just do a numerical diagonalization, and you can do fitting through that. But it's not as exact as what we provided though.
Okay.
Yeah, so I mean, again, these are just transition frequencies between the eigenenergies. That's what these placements are gonna do.
So on that note of his question that he just asked, you have these green and the red that you fit from data, and then that using the calculations you did in the PRB. But I see that you also have these other ones in black that are NMR single crystal. Like, how are those done? What's the significance of those as opposed to the zero field? Like, what did they do? How is it any different?
Right, well, these black lines here, extracted from literature, what they did differently compared to what these guys did, for example, is that they have a single crystal, but they also apply this, they did high field NMR. They have an externally applied magnetic field. But when you do that, you cannot just extract it completely. The Hamiltonian that I gave earlier, the combined Hamiltonian between the Zeeman Hamiltonian and the quadrupolar Hamiltonian, that actually assumes that the internal magnetic field is aligned with one of the BFG principal axes. When you introduce this external magnetic field, you completely complicate the Hamiltonian, especially because the quadrupolar Hamiltonian and the Zeeman Hamiltonian don't commute with each other. And so in order to extract all three parameters, what they have to do is they have to find the EFG transition frequencies. I'm sorry, the NQR, the NMR transition frequencies as a function of a rotation angle with respect to that magnetic field. And so they have to get a whole set of these spectra essentially. Whereas these guys in fact, they don't have an external magnetic field. They have a powder sample. The magnetic field is built into the crystal system. They were able to do it without having to apply a magnetic field and without that unnecessary broadening as well that comes out of it. And they were able to give us this clean data. And so that's why I'm sort of saying that this zero field NMR using powder is somewhat actually superior to what they're doing, because they can't even get all three parameters out because of the difficulty in performing these experiments. Especially you have to have this large magnetic field applied to it in the end.
It's been a while, but can you remind me again how you take these spectra and relate to the experiment again, that is in megahertz?
How do I relate which parts?
Like if I want
Did
to
you put the
compare-
equations anywhere?
I do have the equations, but they're not very meaningful because they're defined in terms of these other things that I've also created. But these are the exact transition frequencies.
So the reason I asked, suppose very basic experiment like X-ray diffraction. If I do X-ray diffraction, I measure it, I go to ICDD database, I match derivative refinement to get a crystal structure, find a lot of structure property from there. How about EFG? What's the process for this? Like I did a measurement, what's the subsequent steps after this experimentally?
An NMR experiment.
Yes, I mean, if I want to calculate EFG or predict EFG or
You want to predict EFG.
not predict, like if I want to measure EFG from that signal that I got from the experiment,
I see.
what's the process?
I see. Well, again, these are the transition frequencies. I would set literally the appropriate ones equal to these fitted transition frequencies, these three peaks here.
So you have to do the peak fitting.
I have to do peak fitting first, extract those transition frequencies and set them equal to the right equations that I
Do
derived.
you have the omega 0, omega plus, and omega minus in terms of the fundamental things? Do you
Not
have
here,
somewhere on the backup slide or something?
I do
No?
not. But yeah, it's
Quite a process.
it's a very straightforward process. We simplify it to a degree that has been done before. The previous papers on this topic, they didn't have the machinery that we have. And no one bothered to do it actually for some reason.
If you could write, do you have them memorized?
Do I have
If
them
if you,
memorized?
if you could write them up, you would see it's not that
It's not,
deep.
okay.
It's not that deep, but
It's not deep at all, actually.
he didn't, I don't have my marker with me.
Yeah.
Maybe it's in the thesis somewhere, I'll take a look.
They're actually, there you go.
So staying on this slide, right? I see you have these angles. You have theta eta and theta prime eta.
That's right.
And what are those? You gave us a table, but what are those? Can you say anything about what theta eta and theta prime eta means?
Certainly. So these are angles that we defined ourselves. We invented them using our machinery. These theta and these theta eta, which you can actually write in terms of theta eta prime, are a qualitative measure of the EFG asymmetry. And so you'll see here that there's no mention of there's no actual mention of eta in any of these equations. The eta is built into this theta eta. And so the way we wrote it out actually is that the tangent of this theta eta is directly proportional to the Vxx minus Vyy, which is proportional to the eta. And so we qualitatively say that theta eta is a measure of EFG asymmetry.
So it's in the spherical coordinate system?
It's not physical whatsoever. These are defined, this is the machinery that we chose in order to.
It's a coordinate system you chose basically, right?
There's no coordinate system, there's no spatial relationship between this theta eta and the actual spherical coordinate theta.
Does anybody have a marker?
Marker would, I think there's a marker
Yeah,
here.
you have a,
Oh, I found a marker.
I just next door.
Yeah, I found a marker.
you have a marker, okay.
So for example, this is just what we defined.
You can do proportional, don't worry about the
Yeah, yeah,
exact things, don't,
Yeah.
it's okay.
Yeah, all we're really saying is that the way we define this thing, is that it's proportional to this Vxx minus Vyy.
Over,
It is over I think 2 omega 0 plus omega q, something like that, yeah. The point is that this was just a way to encode all this information into a single parameter. Or else you'd have to write that all over the place there. It works out in diagonalization. It's a very elegant way of doing it, but we created this as a way to just simplify the mathematics behind it all. There's no spatial connection between this theta eta and what you're seeing there.
And why root 3 cos of that?
Why root 3?
Isn't derived.
I mean, that comes out from, because we did this for spin 3/2, and so that's kind of comes out from there.
so this theta comes from a certain kind of theory, actually.
Comes
Like,
out,
you didn't pull this from your head, actually, what,
unfortunately, I was not the genius who came up with this formalism. This is actually, you can use, you familiar with Cohen and Tanucci, quantum mechanics book, using spin 1/2 formalism, actually. Fictitious spin 1/2 formalism, you can use it to derive this very elegant equation. Essentially, what you do is you assume that you can write your Hamiltonian as 2 subblocks corresponding to 2 components of a fictitious spin 1/2 particle. Using that, you can diagonalize the system as if it was a 2x2, but it's actually 2x2 block matrix. Doing that, you can do it's written out very elegantly in Cohen and Tanucci. You talk about it a lot in the paper as well. But it's a fantastic way of doing it. You can always do it whenever you have non-degenerate energy levels. And if you have degenerate energy levels, you can't do it. But if you have non-degenerate energy levels, you can break up any size matrix you want into a spin 1/2 block matrix. But this was really set up for it really well, because actually what you get is like this combined Hamiltonian, this HQ plus HZ. What you actually get is you get some some matrix here, some matrix here, but these guys are actually 0. And when you have that, when you have this type of configuration, this type of block matrices, you're golden because you can really solve these equations very easily.
This has nothing to do with Majorana.
With what?
Majorana matrix.
Oh, no.
So I mean, just this d theta remind me the mixing angle in, say, neutrino oscillation and stuff.
Yeah, I don't think there's no connection between those guys.
Yeah.
Not yet.
Not yet.
But it does like a block diagonalize into 2x2 systems.
Mhm.
Okay, each one you can introduce theta, eta.
You could, but it may not be the best choice. But I guess theoretically, yeah, you could, but not really. In general, yes, you can do that, yeah.
So what's the use on the parallel transitions? You kind of made this argument that, right, if you go to a previous page, you get 3 lines and you know everything.
Mhm.
So is there any particular use you can make of the parallel transitions? In other words, I'm looking at this and I see kind of complicated expressions using these cosine angles that you were seeing, except for those 2 down there, in which they're not as complicated matrix elements.
That's actually a great question.
Actually, what do the matrix elements mean now that I'm asking the question? Like, why do you have matrix elements?
Why do I have matrix elements?
Yes.
Well, we actually derived a formula for the observed magnetic moment, and they are written in terms of these spin angular momentum operator matrix elements. And so I can actually write it out. We after you recite the system, you come up with a signal, and the signal is proportional to something which has is proportional to something with these and a bunch of other stuff. So they're directly in the observed signal. So that's why we needed those guys. In terms of these parallel transitions, it's a good point that they are much the expressions are much simpler. And so you can see here that the signal for these parallel transitions are directly proportional to this minus sine theta eta, because that's how it is in the signal equation. And so because of this theta eta is directly related to the EFG asymmetry parameter, you can look at your peak heights of your parallel transition. You can immediately you can say something about the EFG asymmetry directly just from those parallel transitions if you can measure them. Unfortunately, it is hard to measure them because you can see here these relative peak heights pretty small compared to the main transition frequencies. They're pretty small, but if you can measure them, you can say a lot about the EFG asymmetry directly from that.
It's hard to measure them directly.
It's hard to measure them directly, that's right.
Any other questions from the committee? Okay, then we kicked the public out now, including including Jafar. Don't go too far away. I don't know if this room, I can see if this room is open.